our ME23, development of a wireless motor sensor for deployment in commercial applications. Looking at the picture from the left, my name is Syed Hussein.
My name is Logan Vidal.
My name is Marika Page.
Our faculty advisor is Professor Giblin, and our industry sponsor was Dr. Wei Zhang of the Harvard Steam Boiler. We're going to start off with the problem statement and the project objectives set by HSB. We're then going to move on to the enclosure development and the design. We're then going to move on to the objectives that we met this year, including what testing we were able to accomplish and the results from that testing. We're then going to move on to summarizing what we were able to finish before the outbreak of COVID-19, and then we'll issue some final recommendations for HSB as well as the university for advancing the project. The objective of this project is to develop an Internet of Things sensor array to monitor AC motor working conditions to reduce the overall risk for HSB's customers by predicting impending failures and providing notice for preventative maintenance. HSB dictated 5 requirements to be measured by the sensor array, including motor on-off condition, surface temperature of the motor casing, vibration signal, rotation speed, and loading. We were able to meet 3 of those conditions as highlighted by the green, and we were still in the progress of developing the last 2 conditions.
Our project design utilizes 3 sensors, a thermocouple, an accelerometer, and a Hall effect sensor. All of these sensors were attached to a PCB or printed circuit board shielding. This shielding was designed by our ECE team and custom manufactured for use in this project. The image on the left is an exploded view showing how the sensors and the other components were layered to fit into the enclosure. From the top layer down is the Arduino PCB shielding, the thermocouple, the Arduino, the accelerometer, and adjacent to all of these components in the enclosure is the battery. The image in the bottom right shows all the components in the 4" by 4" by 2" enclosure. This slide shows our prototype design for attaching the sensor enclosure to the motor's housing. It is a non-intrusive design that utilizes adhesive strips that semi-permanently joins the quarter pipe stands to the motor's rounded design.
Preliminary baseline testing of the motor in phase 1 was conducted in the electrical engineering lab with the motor and motor controller. In phase 2 of the testing, the motor was integrated into the water loop test rig. The data taken in phase 2 was compared to the data taken in phase 1 in order to verify the functionality of the sensors and to validate the results. The graphs on this slide include the X, Y, and Z axis acceleration taken via the accelerometer and the temperature data collected by the thermocouple. A Hall effect sensor was also used to measure the magnetic field strength in order to determine the motor on-off status. These graphs reveal the overall trends of the motor performance. The graphs also demonstrate the user interface platform where the data taken by the sensors is saved and displayed for analysis by Hartford Steam Boiler. The microcontroller Arduino sends the data to a gateway connected to the internet using long-range radio transmission waves. The gateway then uploads the data to the cloud, and it is displayed as shown here. The data shown in the following graphs was collected with the sensors adhered to the motor surface with the motor operating under an external load in order to induce changes in operation. The graph on the left shows the positive correlation between the temperature and the frequency of the motor, thus verifying the ability of the thermocouple to detect changes in the temperature of the motor. The graphs on the right demonstrate the X, Y, and Z vibrations of the motor over time. Comparing the acceleration data taken at 15 Hz and at 55 Hz, we see a significant increase in the range of the vibrations at 55 Hz. The collection of data over time is critical in detecting these large changes in motor performance that indicate the motor health.
So these are our completed milestones for the year. We were able to develop an electronic sensor circuit setup and calibrate that in conjunction with our ECE joint team. We were able to conclude initial testing for baseline conditions of our electric motor. We were able to develop the IoT wireless transmission system and make it fully functional. We were also able to assemble our test rig and conduct preliminary induced load testing and collect the data for that. We were able to 3D print an initial prototype enclosure design. Moving on to our future recommendations for HSB as well as the university, we would also like to thank our sponsor, HSB, as well as the university for providing us a learning experience for this year, and we would like to thank any of you watching as well, the judges. Thank you for watching this presentation.